Hello, this is question 5 from the 2019 MAT. This question is about counting the number of ways of partitioning a set of n elements into subsets, each with at least 2 and at most n elements. If n and k are integers with k between 1 and n inclusive, let f of n and k be the number of ways of partitioning a set of n elements into k subsets. Right. Oh, they're giving us an example. Right, that's good. For example, f(5)(2) equals 10 because the allowable partitions of that, right, so we've got 5 elements, that's what the 5 is telling us, and we're putting them into 2 subsets. So how many ways can we divide these 5 numbers into 2 subsets with at least 2 elements in each subset? Right, okay. Part 1, explain why fnk equals 0 if k is greater than n over 2. Right, so let's think about this then. So we have to have at least 2 elements. We've got n elements. We have to have at least 2 elements in each subset. So we've got k subsets. So if we've got more subsets than half the number of elements, yeah, so that's going to fit with this, that we have to have at least 2. So explain why. If at least 2 elements in each subset, then we can say, so we've got 2 times the number of subsets must be less than or equal to n. It has to be, because otherwise we just can't partition things up. If you do the number of subsets times 2 and it's greater than n, then we just can't actually create all of those subsets. So that's what we have to have for that. So yeah, so that fits with this then. So we can rearrange this. So okay, for f of nk being greater than 0, i.e. we can create k subsets with 2 plus elements. That means that we need k to be less than or equal to n over 2. Therefore, if k is greater than n over 2, fnk equals 0. Right, okay, part 2. What is the value of fn1 and why? So fn1, so we just got one subset. There's only one way we're going to be able to do that, isn't there? Only one way we can get one subset. Is there going to be any trick to this? This seems too obvious. So k is 1. N could be anything from 1 upwards. All right, so there is a trick in this then. Yes, because if n is 1, we can't put 2 into the one subset. So if n is equal to 1, then f of n1 equals 0. If n, I suppose I could just do an else on this, but if n is greater than 1, then fn1 equals 1. Okay, part 3. In forming an allowable partition of 1, 2, all the way up to n plus 1 into subsets of at least 2 elements, we can either pair n plus 1, so the last element, with one other element, leaving n minus 1 elements to deal with, okay, or take an allowable partition of 1 up to n and add n plus 1 to one of the existing subsets, making a subset of size 3 or more. Fair enough. Use this observation to find an equation for fn plus 1k in terms of fn minus 1k minus 1 and fnk. Right, that holds when k is in that range. Okay, this is interesting. Let's just follow what they're saying then. So we can pair n plus 1 with one other element and then have n minus 1 elements to deal with. So if we've got then how is this working? So we're wanting to find an equation for fn plus 1 k. So if we've taken that n plus 1 out, we've now got n minus 1 elements in this. I'm just thinking about the first bullet point here. So it must be to do with this one. So why is the k dropped? Why is the k dropped? Fn minus 1. Oh yeah, because we've already paired it up with one other element. Yeah, we take the n plus 1, we pair it with another element. That's one subset out of our k. So we've got k minus 1 subsets left. So we're going to have fn minus 1, k minus 1. And we're going to have, how many different ways are we going to be able to pair up that n plus 1 element? So that n plus 1 element can go with n different elements. So we're going to have n different ways of doing this. So we could take out n plus 1, we could pair it with a 1, or we could pair it with the 2, we could pair it to the 3, we can pair it all the way up to n. So that's n different ways we can pair the n plus 1. And then it leaves us the f of n minus 1, k minus 1. Right, okay, I'm happy with that. Then for the second one, we can take an allowable partition of that. So that's going to be our fnk. So we're going to be adding on something to do with fnk. And add the n plus 1 to one of the existing subsets, making a subset of size 3 or more, where there are k subsets that we can put the n plus 1 into. So we must have k times that. So, and that holds. Does this have anything to do with it? Why have they got k? Well, we've got a k minus 1 in there, so we have to have that k can't be starting at 1. So they've just bumped it up 1. And it now can't be the same as n. That's does that matter for this formula? No, I don't think it does. So wondering why they've removed that equal sign there. Now k has to be actually less than n. It can't be the same as n. That's interesting. But well, actually, I mean, it can't go up as far as n anyway in this, so it doesn't make any difference. I mean, we're saying we're getting 0 if k is greater than n over 2. So it's not really going to affect matters particularly. It's certainly not going to change the validity of this formula. This is definitely going to be correct regardless of how far k goes up, because we're just getting zeros as soon as we go past the halfway mark. So yeah, I'm happy with this then. So we've got n different ways of pairing up the n plus 1. And in the second one, we've got k different ways of adding it to an existing subset. Right. Use this equation to compute the value of f73. Okay, so f73 is going to be equal to, so that's n and it's k. So we've got, this is going to be a bit annoying, isn't it, going through all of this. So we've got 7, oh, that's an n plus 1 is the 7. So n is 6. 6 lots of f52 plus 3 lots of f6, was it 3? Yes. Okay. And f63 is equal to 5 lots of f42 plus 3 lots of f53. We know f53 is 0. We've gone past the halfway point on there. f42, how many different ways can we divide up 4? That's going to be 3, isn't it? Because let's just double check that. If we've got 1, 2, 3, 4, defining one group is going to fix the other. So we could have a 1, 2, a 1, 3, a 1, 4. There's nothing else we can do with that. There's only 3 different ways. So that must be equal to 3. So we're going to have 15 there. So F63 is 15 and 6F52, that was the one they've given us before, so we've got 10. So that is then equal to F73 is equal to 6 times 10 plus 3 times 15. So 60 plus 45, 105. Good, good. Right, I'm going to need a new sheet for the last part. Where's my mouse gone? Mouse has disappeared for some reason. Right, here we go. Give a formula for F2nn in terms of n when n is greater than or equal to 1. Show is correct. Right, so we're dividing up into pairs. So every subset must have 2 elements in it because we've got double the number of elements of subsets. So yeah, we must have that going on. So how are we gonna do this then? So we've got 2n elements, and we've got 2 elements in each subset. So this is going to be one of these permutation things where we're going to be over counting initially, and then we're going to have to remove some of the permutations. Because say we had 1, 2, let's just start with a simple one. So say we have 1, 2, 3, 4. And we can rearrange this in loads of different ways. 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2, and so on. So we got loads of different ways we can set this up. So, well, we're going to end up getting 4 factorial on this, is what the number of permutations is going to be. You know, I've already done the first batch of 6, and now we can just repeat this again with 2 at the front, 3 at the front, 4 at the front. So we're getting 4 factorial is going to be the number of ways we can arrange that. Then we can pair them off. So if we paired off, say, just as we're going along, so we could say those, we could say those, but that's actually the same, isn't it? That isn't going to be any different because we don't care about the order of the numbers inside each subset. And similarly, we don't care about the order of the subsets either. So if we had another one later on that was going 3, 4, 1, 2, and we divide it up, these two things are actually equivalent. So, right, so how are we going to unpick all of this then? How are we going to unpick all of this? I mean, at least it's just saying give a formula. We don't have to show too much about how, we don't have to give an explanation of how we're working it out. Right, well, the total number of ways we can arrange these 2n elements is 2n factorial. So that's all of it, but that is including the ordering of the numbers and the ordering of the subsets. So we don't care about the order of the numbers in the subset. So for each subset, we're going to be double counting because we're going to have, like in this example here, a 1, 2 or a 2, 1. We've got n subsets, so we're going to have to divide by 2 to the n because each subset has got 2 permutations and we only want it to have 1 permutation. So we've got to divide by that. So that deals with that. And then we've got the order of the subsets. So how many ways can we order n subsets? So that would be an n factorial. So we've got 2n factorial on the top because that's how many different ways we can arrange the elements. We got an n factorial on the bottom because that's the number of different ways we can order the subsets. And then we got that 2 to the n on the bottom because we don't care about the order of the elements inside each subset. Right, yes, that's fine. That comes out okay. So that is f2n comma n is equal to that. The providing we've got, and what happens then if n goes, oh well, it can't go beyond this, can it, because it's defined in terms of n, so we don't have to worry about that case. So that's fine. Show it's correct. Show it's correct. Well, we did do earlier on, we did an f6.3 and an f4.2. We know these already. f4.2 was 3, f6.3, well, that was the 15 one, wasn't it? Because we multiplied that by 3 to get 45. So let's show these then. So f6.3, So 6 is our 2n, so we want to have 6 factorial over 2 to the power of 3, and then 3 factorial. So that is going to be equal to 6 times 5 times 4 divided by 8. So 15, because that'll leave a 3, that's taking an 8 out. 3 times 15, so that's fine. And then this one would have 4 factorial over 2 to the power, not 2 to the power of 2, not 4, and then 2 factorial. So that would be equal to 4 times 3 divided by 4, which is 3. I mean, I don't know how many of these they'd want to show, but I mean, at least it's shown that it's correct for those two. So, yeah, I mean, I don't know. It's like how long's a piece of string on showing that the formula is actually correct. But maybe that's going to be sufficient, just picking out those couple of examples. I mean, do we have to do the next one up? I mean, if we were going to do F8,4 out of that, actually work out what it is, or is that just going to be a bit of a mess? Yeah, what was it? F8,4. Then maybe if we had one more of them. I think I can't remember what the blank formula was now. It was, what was it? N, that was our n plus 1. So we had to go down to say it was going to be 7 lots of F6,3, which we know, plus then 4 lots of F, would it then been 7,4, wouldn't it? Which 7,4 is going to be 0. All right, so is that just what we're getting? We're just getting 7 lots of 15. Is that going to be right? Well, I'll see what happens if we put it into the formula. I might have misremembered this bit. If it doesn't end up matching, I'll have to go back and double check. So we'd have 8 factorial divided by 2 to the power of 4 and 4 factorial. So that will be 8 times 7 times 6 times 5 divided by, well, 2 times 8. So we can cancel those. Cancel that to leave a 3, which means we've got 7 times 15, which is 7 lots of F6,3. Right, so I mean, that's 3 examples of it working. Like I say, I mean, if they want something else, I'm not too sure how I'm going to show categorically that that's going to work for every single number, but at least it's shown, you know, the first 3 of them. So yeah, that seems good enough, I think. Yeah, that question went through fairly quickly, I would say. The opening couple of parts were fairly straightforward. The middle bit, at least they held our hands. That would have been quite difficult, but they gave the 2 cases to just flesh out in order to create that formula. And then the last couple of parts, the last part I did like working out that formula. It just takes a bit of thinking through with the permutations, but it's the sort of thing that you're probably familiar with if you've set up the formula for the choose numbers and things like that. It's got a similar part of it, where we're looking at all permutations and then removing some of them as being double counted. So that's why it's quite easy to then drop in, if you're familiar with that anyway. It's comparatively easy to then drop into doing that, get our full list of completely unique combinations, and then just skim out the duplicates that we don't particularly need in this case. So it's something that you may well have come across before, as I say, with those choose numbers. But yeah, nice little question, that one.